Hi everyone, it's Dr. Schultz, and in this video lesson I'm going to go through the basics of determining the electric potential of different charge distributions. And I'm going to do this in an APPhysicsLectures.com kind of a style here by taking my notes directly into the video. So far in this class we have looked at point charges, and we've focused on point charges as a source of electric potential. What we're going to do now is actually look at what happens if charge gets spread out or distributed along some type of a shape. And the question is going to be, can we determine an expression for the electric potential of different charge distributions? The answer, of course, is yes, we can. And we're going to look at two different categories of charge distributions that can be dealt with mathematics. In the first case, you can consider charge distributions in which the charge is highly symmetric in the way that it's spread around. And in the second case, we can look at cases where the charge produces an electric field which is highly symmetric in its properties. Okay. In the case of the charge being highly symmetric, the approach that we're going to use is basically to integrate the point charge potential. So we're going to determine the electric potential by doing an integral of K dq over R. Okay. And you should recognize that the expression inside the integral is the electric potential for a single point charge. So when we take an integral of that expression, we're going to be adding up the contributions of a large number of point charges to find the total electric potential. Okay. This is actually what we're going to do in the lesson right now. Okay, so this is the purpose of this video. Tomorrow we're going to learn about the other case, which is if you have highly symmetric electrical fields, and in that case we're going to be deriving expressions for a change in potential between 2 points. And we will learn about what's called a path integral. Okay, so this is going to be later. And so today we're going to focus on highly symmetric charge distributions. Alright, well, let's do two examples today. The first example is going to be a charged ring. Okay. So example 1. This is going to be a uniform ring of charge. Okay. We've seen this particular geometry before. I'm going to sketch the ring. And I'm going to draw an axis, its primary axis of symmetry. The radius of the ring is going to be A, and we are going to try to find the potential at a point P along that axis of symmetry. So our goal is to derive the potential as a function of x, where x is the distance from the center of the ring. Okay. So if you take a look at this picture, let's think about this from a calculus point of view. We're going to assume that that ring is made up of a large number of small chunks of charge. We're going to call the chunk dq, and then we're going to express the distance from the chunk to point P, and that's going to be the hypotenuse of that triangle. Okay, so it's very similar to what we did before with the electrical field. Okay, so let's go ahead and set this up. So in this particular distribution, you'll see that the charges are uniformly distributed around the ring. So this is a really symmetrical case for the charges. And so I'm going to start off by writing out our integral, and we're going to be trying to add up the individual electric potentials from all of the little chunks on the ring. Okay. All right. Well, one thing that you by now should see, having done several of these ring examples, is that the distance, the diagonal distance from the charge to this point, will not change. In other words, as you look at different DQs around the ring, they're always going to have the exact same distance to that point P. And so we can actually take some things out of the integral here. Okay. So I'm going to bump my integral sign over. Of course, K is a constant that can come out. And my R is going to be this distance, my diagonal distance. So that is a squared plus x squared, square root. And so all that comes out because a is a constant and x is a constant. And then that leaves me, with the world's easiest integral, which is just the integral of a variable. And so what I would do then is evaluate that by going all the way around the ring and adding up all those charges. And I arrive at my result, which is that the potential at a distance x along the primary axis of symmetry is going to be equal to K times the total charge divided by the square root of a squared plus x squared. Okay, so that Q total is the charge that's placed on the ring and that's spread out evenly, and that's the answer. Okay, so it's a pretty straightforward answer to get. One of the interesting applications of this is to look at x is equal to 0. In other words, the center of the ring. And of course, if you look at the potential there, the expression that we derived gets real simple. And it simply becomes K times Q total divided by the radius of the ring. Okay. So sometimes in problems, a lot of times you look at what's happening at the very center of a symmetrical object. That's a pretty simple formula for calculating the potential right at the center of the ring. So it's a useful thing to do. All right. At this point, I'm going to have you practice with the problem. A little example here for yourself. And here's the example. I'm going to give you 2 rings. And we'll make the smaller ring positive. Okay. We're going to give that a charge of plus 100 nanocoulombs. And then we're going to make the outside ring negative. And I'm going to make that negative charge negative 200 nanocoulombs. All right, so it has twice as much charge on it spread around. Now, for the radiuses of these rings, let's make the inside radius equal to A, and let's make the outside radius twice as big. Okay. And of course the rings are both on this, they're centered together, they're concentric. So what I'd like you to do is, first of all, I'd like you to find the potential of the small ring at the center. Alright, so for x is equal to 0, I'd like you to go ahead and calculate the potential that only the small ring creates by itself. Okay. Then I'd like you to go ahead and do the same for the larger ring. Okay, and I'm going to let you do that. You might want to pause the video right now, pull out a calculator and figure that out. I need to provide you with a little bit of information here. We're going to make A equal to 20 centimeters, so you'll have to use that to figure out your potentials. So go ahead and pause the video, pull out your calculator and figure out those two potentials, and we'll check back in a minute. Okay, so now you've had a chance to work those out. What's kind of interesting on these is that the potentials turn out to be basically the same magnitude but opposite signs. So the small ring will generate a potential of plus 4,500 volts at the center all by itself. The large ring will generate a negative potential because it's negatively charged, and that would be negative 4,500 volts. And I hope you can see the reason is because you've got twice as much charge on the large ring, but it also has twice the radius. So those two things kind of cancel out. So if you ask the question, what is the kind of, what is the net potential, at the center, yes, those two things would combine to cancel out and give 0. Okay, so the total V net would be 0 volts. So you can do that sort of a thing. You can actually, if you have multiple different objects, you can add up the potentials that they contribute separately to determine the overall potential at a point. Okay. All right. We'll do one last example of a geometry that you can work with this technique. And the last example is going to be the line segment Okay, we've seen this the geometry before. We've got a line segment. The length is going to be equal to 2a. This line here is the bisecting line, and we're going to be looking at a distance x away from the line. We'll call that point P. And again, the goal is to find the potential as a function of that position x. Okay. So let's take a look at this. This is a little bit less symmetric than the other example. Now what I'll be doing is I'm going to be looking at my chunks of charge, my dq. Those are going to go up and down. That chunk of charge is going to be located at a position y above or below the x-axis, and its thickness is going to be dy. And we want to look at how that chunk contributes some potential at this point P. So we're going to be looking again at the diagonal distance. That distance is going to be x squared plus y squared, square root. So that's the Pythagorean theorem. Yeah. Okay. So those are the parameters for this problem. We did a similar integral with electrical fields. However, this is not a vector integral anymore. This is a scalar integral, and it's a little bit easier to deal with things. So we are not going to be talking about like components of the voltage. There is no x component, there is no y component. Okay, so that's important. No x or y components of V. It's a scalar. Okay, so that's an important difference from the type of problem that we did before for electric field. Let's write down our expression here. This is a symmetric charge distribution, so I'm going to have a voltage now which is going to be determined by integrating k dq over r, but in this case my r is complicated. I hope you can see that as I move up and down the rod, my y value is going to be changing. Okay, so y is not a constant. Okay, and so I cannot factor that term out of the integral like I did before, which is kind of a bummer. Okay, so off to the side here, I got to figure out what to do. I hope that what you're thinking about is I want to actually get rid of this dq, and I want to replace it with something like dy, because I can let dy range from plus a to minus a. Okay, so I'm going to do something off to the side here. If you take this rod and you say that it has some total charge on it, q, then that charge density is going to be equal to the charge divided by the total length. So lambda is q over 2a. And since we're saying that this is uniform, we can set that equal to dq dy. Okay. Now this is going to be the trick that allows us to substitute and get rid of dq in the integral, because this becomes that, and I can go ahead and pull that in. And so now I've changed my integral from an integral of charge to an integral in terms of the vertical height. So I can now put endpoints on this, because I'm going to integrate y from negative a to positive a to finish this up. Okay. So that's good. What's bad is that this is a complicated integral to solve, so we're going to use an integral table for that. And I'm not going to pull that up right here or right now. I'm just going to go right to the result, which is kind of complicated mathematically. So I just wanted you to see the process for how to do this. So the final answer for this one comes out to be kq over 2a, and then that integral turns into the natural log of all this stuff, a plus a squared plus x squared over negative a plus a squared plus x squared. And that's your answer. Okay. Oops. So it's not a very pretty answer, for sure, but the process of setting it up is very important, and you can calculate this, you can calculate the potential simply by plugging things into this. So it's really not a bad thing to deal with, as long as you've got a trustworthy calculator and you can use it. Okay, so let's wrap it up here. Today what we've done is we've looked at a technique for determining the electric potential in situations where you have highly symmetric charge distributions. Things like taking charge and putting it on a ring, or taking the charge and spreading it out along a line. So we kind of went through and showed that it's extremely easy to deal with the ring case. It's a very easy integral, a very nice simple result. And then looking at the line case, as we saw before, it's a little less simple because the line is actually less symmetric than the ring, the line segment, I should say. So we get a slightly more complicated answer, but the process itself is, hopefully it makes sense to you. We aren't really going to use this technique for many more situations. In fact, as we finish up this unit, we're going to spend most of our time looking at the second way of solving for the electric potential. So we're going to start into that tomorrow, but it's important that you at least know how to use this first technique to solve several simple geometries. Okay, so please go ahead and check out the next video on apphysicslectures.com, and that will help you out with getting started with this. All right, have fun.